So in Unit 7, we did exponential functions. So that would be questions like if I said, what's x? What's x? Well,
Yeah.
versus. Yes, it is 2. Okay? It's, sorry. No, that's not what I. Yeah, 2, okay. Confusing myself after I wrote that. So what's this? It's a decimal. It's 1 point something, right? Because if 2 to the 1 is 2, 2 to the 2 is 4, that means 2 to the something between 1 and 2, okay? 1 point something must be 3. But how do we get an exact answer? This is where we use something called logs, okay? They're called logarithms, but we always say logs for short. So, how do we get to logs? Well, first of all, every operation has an inverse operation. In other words, a way to undo it. So how do you undo addition? Subtraction. How do you undo multiplication? Division. How do you undo squaring something to get back? Square root. So these are all examples of inverse operations. An inverse of an exponential function or equation, okay, is what we call a logarithmic equation. And here's how we get there. And once we learn how to do these things, which we're going to start today, and we'll see what their graphs look like. Okay, then we're going to start. There's some other stuff we need to do before we start doing log equations and log problems. All right, so we've got here an exponential equation. C to the x equals y. Okay, and we could graph it, right? If there were all numbers there and one was unknown, we could solve for it. The inverse, how do you find the inverse of an equation? What do you always do? The what? How do I find the inverse? I switch the x and y. So the inverse looks like this. But then I got to solve for y. Well, this is kind of weird. You haven't seen anything like this before. Okay? To solve for y, we actually have to take the log of the base c of x. And c has to be a positive number other than 1. Okay, we can't use negatives, we'll see that. Okay, we can't use 0. So how do we practice going from exponential form to log form? So these two are inverses of each other. Well, notice how in exponential form, the base becomes the base of the log. Those are the base. The exponent becomes the answer to the log. And the answer to the exponent becomes what we're taking the log of. So like if I said, and we'll do some practice. If I said 2 to the 3 equals 8, that's an exponential equation. How do I convert this to a logarithmic equation? Well, I write log. The base of this equation becomes the base of the log. The answer to this, sorry, I'm going to make sure I'm right here. And sorry, I was just making sure I was recording as well. The exponent in exponential form becomes the answer to the log. And then the answer to the exponent becomes what we're taking the log of. And we can convert from one form back to the other. Okay? Because what's the whole purpose of a log? We're trying to find a missing exponent, like we tried up there. Okay? A log helps us find missing exponents. Logs have a bunch of different bases. If a log has a base of 10, we call it a common logarithm. When you see a log written without a base, you always assume it's 10. Okay? Unless there's another number written as the base. Okay, so I showed you how to go from exponential equation to logarithmic equation. Let's go the other way around. How do we write these equations in exponential form? 5 to the power of 3 equals 125. Okay, good. Because remember, the base of the log becomes the base of the exponent. The answer to the log becomes the exponent. What we're taking the log of becomes the answer of the exponential. Or, I mean, another way you can look at it is if you draw a cursive E. If you're changing this to exponent form, start here and draw a cursive E. So log base 5 to the 3 equals 125. Just a little bit. You don't have to really worry about that. And notice that the exponential form actually makes sense. 5 to the 3rd is 125. So if you did it incorrectly, like let's say if you did this by mistake, you should be able to recognize that you made a mistake. Because 3 to the 5th, no, that's not 125. That doesn't make any sense. So I must have made a mistake. How about this one?
3 to the power of 4 equals 81.
And that's true because 3 times 3 times 3 times 3 is 81. What's the base here? 10. And therefore the exponential form is 10 to the power of 2 equals 100. Which is in fact true. 10 squared is 100. How about this one? E to the n equals q. Okay. Obviously, we can't check that one unless we knew what those what numbers those letters represent. How do we go back the other way? Well, we know it's log. Base and exponent equals base in log. So those will always match up. And then remember what comes next? 16 equals 4. Because really what you're doing with a log is you're asking yourself, okay, if I'm doing 2 to the something is equal to 16, what's the answer? That's really what it's saying. Log means 2 to the what is 16, and the answer is 4. This one? X. This one? Log 2 of 1/8 equals -3. And log A of n equals m. Remember, the exponent in exponential form is always equal to the answer in the log. Okay, so now that we know that, we can actually solve log equations. So here, we can actually take it one step further and say, okay, log base 2 of 32 is equal to what? Well, change it to exponent form. Now, what does this look like in exponent form? 2 to the y is equal to 32. So what exponent 2 to the what is 32? 5. So y is 5. Change this to exponent. Well, I get 9 to the y equals 3. Ooh. That's a weird one. Can you think of a relationship between 9 and 3 to get from 9 to 3? Square root. Do you remember what square root is as an exponent? 1/2. Good. Well, this one, when you change it to exponent form, it's going to look like this. This time, the missing item is not the exponent, it's the answer to 4 to the -2nd. Whatever that answer is, which would be, well, what's 4 to the +2nd? What's 4 to the -2nd? Non-negative. Fraction exponents mean, sorry, negative exponents mean fraction. 1/16. How would you write this one? 10 to the 1 equals x. Well, 10 to the 1 is what? Yeah, that's it. And finally, this would be 2 to the x equals -4. Not 1/2. It's not the square root. There's no, you can't do it. Because if I did 2 to the 1/2, that's the same as square root of 2. That's not 4. If I did 2 to the -2, isn't that the same as 1/4? Not -4. Okay, so yeah, there's no solution. We can't do it. A couple of ones that you can get very quickly. Whenever you take, no matter what the base is, the log base, whatever number of 0, did it again. The log base of 1 is always, I just said, 0. Because think about it like this. See, if I change this to exponent form, I'm asking myself c to the y equals 1. What must y be?
0.
It has to be 0, right? Okay. What about log base c of c? In other words, c to the what equals c, 1. So whenever the base, and this is called the argument, by the way. That's the fancy name for it. Whenever the base and the argument are the same, it's 1. Whenever the argument is 1, it's 0. And this one, well, if you think of this in the exponent form, c to the, whatever the answer is, I'm calling it y, equals c to the x. Well, that means it must be x. Right? Because c to the x equals c to the x. But those, I mean, you don't really have to worry too much about those. As long as you are able to convert it to exponential form, you should be able to figure it out. Okay, the last thing we're going to look at here is what do the graphs of log functions look like? Okay. Well, we know how to graph y equals 2 to the x. Okay. Remember the x's I chose, I told you to choose? -1, 0, 1 for exponential. Because 2 to the -1 is a half. 2 to the 0 is 1. 2 to the 1 is 2. So that means we get -1 is 1/2. So here, 0 is 1. 1 is 2. What does the left side of this graph look like again? Do you remember? How does it go? Like, does it go through like that? It goes along the x-axis because it never hits 0, but we have to draw something at the x-axis. Remember, we have to draw this line that the exponential function will approach but never touch, which is called an asymptote. So remember, an exponential function consists of not only the curve, but the asymptote. Well, do you remember how to find an inverse on a graph? Switch the x and y's. So if we wanted to see what the log function looked like, well, -1, 1/2 would become 1/2 -1. So this one becomes this one. This one, 0, 1, becomes 1, 0. And this one, 1, 2, becomes 2, 1. And you should be able to see the way the curve goes. What do you think is going to happen as it goes down? Is it going to cross the y-axis? No. It's actually going to hit, or sorry, going to run along or approach a vertical asymptote. Those two are inverses of each other. And how can you always tell? Well, they will always flip over the diagonal line y equals x. So it's like taking the exponential one, tilting your head at 45 degrees and flipping it. So therefore, y equals all of these points on the table of values will be reversed. Oops. Reverse this. So -1/2 will become half -1. 0, 1 becomes 1, 0. 1, 2 becomes 2, 1. So that's one way that you can graph logs. Whenever I see I'm asked to graph a log, and this one would be log base 10 of x. Whenever you're asked to graph something like this, change it to exponential form and do a table of values for that. Okay? So whenever I see this, I'm going to say, okay, I'm going to see what y equals 10 to the x looks like. And what are the 3 points? -1, 0, 1. Which is 1/10, 1. Sorry, what am I doing here? I'm mixing things up. Try to see. -1 gives me 1/10. 0 gives me 1. 1 gives me 10. And now, to get to the log function, reverse it. So just remember, we're doing the log one. This is the one we want to graph. So just reverse these. I know it's 2 table of values, but I'm sure you can do it. Okay. Otherwise, it's a little difficult to sort of figure out a table for logs. I always find if you take the exponential one first and then reverse all the table, reverse the columns in the table, it works a little bit easier. So remember, this is the one I want. You don't have to graph this. You don't have to graph that. You only have to graph these. So we've got 1, 2, 4, 5, 6, 7, 8, 9, 10. And then we got 1, 2. I don't really need to go much further than that. Nope. So 1/10, which is really close to the origin, is -1. So it'd be really close to here. 1, 0. Well, just like 0, 1 always exists on a exponential function, 1, 0 always exists on a logarithmic function. And then 10, 1, which is way out here. So you can see it takes a way sharper curve. But there's still a vertical asymptote here. So it's going to take a really sharp curve. So remember, when you sketch a logarithmic function, put a table for the exponential one, and then reverse all the x and y's, graph it, make sure the vertical asymptote is there. And then just to summarize the properties. Okay. Each graph in this form, as long as there's no transformations done to it, will always go through the point 1, 0, just like exponential ones go through 0, 1. And in exponential ones, 0, 1 was the y-intercept, and logarithmic ones, 1, 0 is the x-intercept. Remember, the exponential one had an asymptote on the x-axis, so x never got to 0. So there was no x-intercept. Here, it's the reverse. There's no y-intercept. The domain and range you can get from the graph. Well, the domain would be what? 0 to infinity. What do I put around the 0? You sure? The curved one, right? Because it never includes 0. Never touches x equals 0. Gets really close to it. And the range? Yeah. Everything. And like I said, with exponential functions, there was a horizontal asymptote. With logarithmic functions, there is a vertical asymptote, and it would be at x equals 0. The vertical line x equals 0, which is the y-axis. Big area where logarithmic functions were used was during COVID. They could actually model the growth of COVID using a logarithmic function the most accurately. Okay, so I mean, it did have a very important use. A lot of the graphs that you saw showing what was happening were logarithmic ones. Okay,